Yes, it is clear.
Okay, sir. Then a very good evening to all of you, and including to Professor Lucas, one of my respected lecturers. It's glad to see you, sir, in the audience. What I would do is in the next 1.5 to 2 hours to come, I will give you a very quick overview of the Sri Lankan power system, the present power system, and also the future power system that you would work one day when you come to my age. The things are changing very rapidly. We are actually in a very critical stage of the expansion of the power system, and the future power system would be a lot different to the one that you see today, and one that would there exist during the last 100 years. So I will touch upon the type of power system that you would expect in the years to come. And also I will briefly take you through the Sri Lankan power system and also how the Sri Lankan power system is operated. If you see my title slide, you will see two pictures on the backdrop. The one on the left, top left, is the former National Control Center where I used to work for about almost close to 9 years. And the one you see at the bottom is the new National Control Center, which is now at Sri Jayawardenepura, which is controlling the Sri Lankan power system. Before I start my presentation proper, let me tell you that my presentation slides will be very simple. Right? Normally, my presentations are quite simple because it is the basics and the fundamentals of any subject that is very important. It's not the big. I will not tell you any big formulas or any big theories because there are academics out there who can do a better job than me on that. But I will give you the practical aspect of it. Things, for example, in the days of the internet, the subject content, the numbers. Now I will be showing certain numbers during my presentation with you, but don't take much attention to those numbers. Don't try to remember those numbers because those numbers are changing. I'm presenting those numbers only to deliver a certain message to you. Because in the days of the internet, unlike in the past, nowadays, information doesn't have much of a value, right? Subject content doesn't have much of a value because it's a matter of going to Google bar and search something on the Google bar. You will get enough subject content, enough material, but there is a certain knowledge that there is a certain understanding that you must have in order to add value to the content that is widely available. The information is available, but you have to have a certain knowledge with you in order to take use of those information, to take use of those subject content. So it is that component that I will be sharing with you in the next 1.5 hours. And also I will try to leave as much time as possible for you to ask questions. You can ask any question. I know there are a lot of things are being discussed in the society pertaining to power system. You can ask any of these things. I will try to share with you as much as possible. Because as I normally tell CEB engineers, I'm doing these lectures one full day for CEB engineers. One thing that I say to them at the very beginning, I will tell you also that sometimes this may be the first time that you will be hearing some of these things, and this could well be the last time. Last time, not because we are living in dangerous times, but because even though you join CEB, unless you ended up at the National Control Center, or even if you become a generation planner, I'm now an expansion planner, you would not get exposed to certain things that I'm going to share with you. So as a result, try to get the maximum out of this session. You can ask any questions at the end. I will open out for discussions. So try to get maximum out of what I will be sharing with you in very limited time, because this is a very broad subject, but this is a very interesting subject. Unfortunately, we only have about 2 hours, less than 2 hours. So I'll try to take you maximum through the Sri Lankan power system. So what I will do is I will first share with you few essential fundamentals to start with. Few very fundamental. I know most of you are first year and second year students, and you are not still aware of the core subjects. So I will not burden you with understanding any deep subject matter, but few very simple fundamentals. And then in the second part, I will give you an overview of the Sri Lankan power system, the present power system, how it is operated. I will very briefly give you an overview, and also very importantly, how it is operated. Because a lot of people don't know this. So I will try to tell you how the Sri Lankan power system is operated. And in the last part, the number is, there's a mistake. In the third part, I will tell you what would be the future power system. I will tell you how we are planning, how we do the expansion planning, and where we want to heading, where we are heading. So I will share that part in the third part of the presentation. So let me start with the fundamentals. If I tell you something very simple, which all of you know, but just for the sake of completion, even with CB engineers, I start with these very simple things. These are simple, but quite important. Let's think there is a person who want to have some water to get rid of his thirst. So there is a certain volume of water that he require to consume, and to that he requires a certain rate at which water to come through his tap. If somebody asks me what is energy and what is power, there is the analogy that I like to take to explain that is water. For example, if I say that the volume of water is equal to energy, the amount of water that you need to consume is equal to energy. Of course, we know that water is measured in liters. If you take the same unit, the power is actually the rate at which the water flows through this tap, which is measured in megawatts. So that is very simple. You all know that. So in a power system, we measure energy usually in gigawatt hours, but the standard unit of measurement is kilowatt hours. And we measure power in megawatts. So not only we have to fulfill his thirst by giving him a certain number of energy units or certain volume of water, but we also have to supply him at a certain rate at which he can consume this water. So both these factors are very important when you're operating a power system. Because, for example, even if we give him the amount of water that the volume of water that he requires, still you will all agree with me that if we give that water something like this, that is not good enough. So keep that in mind in understanding how we operate a power system. Sometimes you may think that this is an exaggerated diagram, but listen to the end of my presentation, you will see that these are becoming a reality. So in other words, if you take a power system and if you want to give this person certain number of energy units, which is equal to a volume of water, we also have to match the power generation exactly to match the demand, or the rate at which he consumes must be equal to the rate at which we supply water, or in my case, power. So the power in megawatts that we generate, forget about the losses in between, must be equal to the amount, the power, the rate at which he consumes, or the power he consumes. It's not only the energy units, but the power generation and power demand must match together. So if I again put this into a very simple diagram, which I like very much, if I put the power demand on one side of the balance scale, which representing consumers, we must exactly match the power demand of the consumers by putting generating equal amount of power on the right hand side of the balance scale, or else what you know as the system frequency will change. The person at the middle, this diagram actually is belong to the Swedish national grid operator. This letters denote Svenska kraftnät. This diagram is about, I think it's about 12, 13 years old. I scanned it from a magazine of the Swedish grid operator, but this is a very beautiful diagram. This shows that in a power system, we have to maintain the power balance in real time. That is the important thing. Power generated must be equal to power demand. Of course, for a full technical audience, this diagram is not exactly correct. Professor Lucas will later on tell you when he teaches you power systems that actually in a power system, these can be when they are in balance, they can settle down at a frequency less than 50, but not according to this diagram. But for a layman audience, this is good enough. So let's now see what is happening. How do we make this balance? So listen carefully. This is something simple, but this is a lot of people, we don't understand it. So let's try to understand what is happening in our power system right now. What is happening in our country, our power system right now. In order for you to understand, what I will do is I will freeze time. I will pause the time that is advancing in front of us. I will freeze the time. And out of the time that is frozen by me, I will take just 1 second block out of it. And we will see what is happening during this 1 second block. So even though you have not still studied your electrical engineering essentials, you all know from your basics that electricity is a form of energy. And we all know that electricity in the form of alternating current or AC cannot be stored. And we also know that energy cannot be neither created nor destroyed. So keeping those three principles in mind, that electricity in the form of AC cannot be stored, let's now see what is happening during this 1 second block that I have frozen, right? So I will take this 1 second block. During this 1 second block, electricity consumers in this country demand certain, they have a certain demand for electricity in terms of energy. So if I say that the demand for electrical energy during this 1 second block at this time, at present time, is 2000 megajoules. Of course, we don't measure electrical energy in megajoules, but there's no harm in doing that. What is your guess? How much do you think I should supply them? Should I supply exactly 2000 megajoules, or should I supply, can I supply less and ask them to wait for about few seconds before I supply them the balance? Or can I supply more? If you're a live audience, I would have asked these questions from you, allow you to think for a few minutes before I get the answer. Because normally I ask these questions not to test your knowledge, but for you to think before I give you the answer, because then only you learn, right? Learning is not about simply memorizing. It's about understanding, comprehending something. So my question again is that if I freeze the time that is advancing in front of us, take a 1 second block out of it. During this 1 second block, let's say the consumers in this country are now demanding 2000 megajoules. And if you are the grid operator, how much do you think we have to give? Exactly 2000 megajoules. Can you give less or can you give more? Of course, if you say you can give more, you can give 2010 or 2030, you must tell me where the balance energy go. So you already know by now that you cannot store electricity in AC form. So that answer is not correct. If somebody thinks that we can supply less than 2000 megawatts and ask him to wait for a few seconds, let's say we supply him 1970 megajoules. To make it easier, I will work with megawatts, because megajoules within seconds is megawatts, right? You know that joules per second is megawatts. So what I'm actually asking you is, if consumers are asking 2000 megawatts, what power I should supply? So if somebody else give me the answer that we can supply a little less and ask him to wait for a few seconds before I give the balance, even that is also not correct, because I am sure none of you have experienced a situation where, now unlike when you open a tap and it takes some time for the water to come out, you never experience something like that in electricity. So the moment you switch on, you get supply. So in other words, I'm sure all of you will agree with me that in the power system right now, in this 1 second block that I have frozen, if the consumers are demanding 2000 megawatts, the power system, the CEB, has to exactly supply 2000 megawatts, not a megawatt less or more. Right? I'm sure that you all would be agreeing with me by now. With that, let's go to the next 1 second block. Right? So first 1 second block, now it is clear, but let's go to the next 1 second block. Let's say in the next 1 second block, my demand had instantaneously increased by 50 megawatts. It can happen, right? It can happen. If the power system demand, later on we'll see how the demand varies. But this can very well happen. Demand for electricity can go up almost instantaneously from another 1 second to the next second. So if now my question during this the second 1 second block is that how much are we giving these consumers in the next 1 second block? So you will again tell me that you have to give 2050 megawatts. If we give 2000 in the first 1 second block, you have to give 2050 megawatts in the second 1 second block. But then I would ask you a follow-up question. This supply is given by generators, right? And you all know that a generator is coupled to a prime mover. Prime mover is the device that is giving the generator the mechanical power, and generator is converting that mechanical power into electricity. That is how this electricity comes out of the generator terminals. So during this previous 1 second block, my prime mover was giving only 2000 megawatts of mechanical power to the generator. Forget about the generator losses for the time being. So during the first 1 second block, my generator is getting 2000 from the prime mover. It is giving out 2000 megawatts from its terminals. And that is how the consumers were getting 2000 megawatts. But in the next 1 second block, when all of a sudden consumers have increased 2050 megawatts, the electricity demand to increase to 2050 megawatts. If you say that my generator now has to generate 2050 megawatts from the terminals, now there is a problem because no prime mover that we know can instantaneously increase the output by 50 megawatts. In fact, generators can. How it is happening, I will not tell you. It's not the time. I don't have the time. But take it from me. If you're not sure, I can give you textbook references. The generators can increase their output, electrical power output, almost instantaneously to follow the demand of consumers connected to its terminals. So, in effect, my generator is now giving 2050 megawatts, but the generator is not getting 2050 megawatt from the prime mover. So how is it possible? Now, how this is possible? This is where a very important concept comes, which called the kinetic energy. In fact, how this is happening is, even though the prime mover is not supplying the generator with this balance 50 megawatts, what is happening is the stored kinetic energy in all the rotating parts of the system are getting converted to electricity during these supply-demand imbalances on either side of the generators. So it is the kinetic energy that is supplying the shortfall and making this shortfall balance, so that until the prime mover again increases output, still the generator can provide the 50 megawatt or 2050 megawatt, the additional 50 megawatt the consumers are demanding. So you all know from your fundamentals that stored kinetic energy in a rotating mass is equal to half I omega squared, I being the inertia. In other words, if your power system has very high inertia, your generator prime mover combination can give this 50 megawatts by a very small speed reduction, delta omega, because your inertia is high. But on the other hand, if the total inertia of all the machines connected to a power system is very low, in order to provide this I omega squared within a certain time period, you have to have a larger omega difference, larger delta omega difference in order to give. In other words, I just only want to tell you that the inertia of machines connected to a power system is very important in order to meet this real-time supply-demand balance, because it is the connected inertia that is doing this without any human intervention during the real time. You also may know by now, or you may learn in the future, that the rotational speeds of all the machines connected is directly connected to the frequency of supply. In other words, if the system frequency is system inertia is high, the frequency fluctuations of a power system is low. But on the other hand, if the connected inertia is low, you can expect frequency changes when the demand changes or there are other disturbances in the power system. So I just want to give you with something very simple. If you don't understand, still don't worry. You will understand the rest of my presentation. But I just want to tell you, in the future power system that you would inherit one day, your system inertia would be very, very low, because all the new power stations that are coming up, solar, whether it be solar power or whether it be wind power, they don't contribute any mechanical inertia. Even though you see the large wind turbine blades rotating, they don't carry any inertia because they have power electronic interfaces. So I just want to keep let you know that fact, because we are thinking about the future power system as well, right? With that, let's move on to, and also you must know that the frequency is maintained within a very tight band. For example, we maintain frequency within plus or minus 1% band. Our system frequency is 50 Hertz. We only allow 49.5 to 50.5, very tight band. Right. Then this is, if I put all the activities that are taking place in a power system, this is the real time. This is not drawn to a scale. Now you know what is happening on real time, but you know that now still when the mechanical inertia, let's now see what is the next activity that is happening in a power system. Very quickly, I will not go into detail. Real time, the mechanical inertia or the kinetic energy help me, but we can't go on like that because machines will slow down. So very soon there has to be another activity which is called the governor action. So if I draw very quickly, show you a frequency time diagram. If my frequency was 50 Hertz, and when my demand all of a sudden goes up by 50 megawatts, if there are no governors, still the frequency would settle down at a certain value. I will not tell you why, I don't have time. But if there are governors, frequency will not get back to 50, but frequency will settle down at a value which is very close to the normal frequency with a frequency error. So that is what the governors would do. Governors will not bring the frequency back to 50, but it will settle it down at another value which is closer to 50. That means there has to be another activity to bring the frequency back to 50 Hertz. So that is what we call frequency control. Right? There's another activity taking place in a power system called frequency control. Frequency control, when the governors bring the power back to within a certain value, frequency control will bring it up to 50. So this you will later learn when you learn in power systems, that this is called automatic load frequency control, the primary load frequency control. This is called the secondary load frequency control. I will not go beyond that explanation because I'm not here to teach you theory. Then how is the frequency controlling done in Sri Lanka? Very quickly, I will tell you. There are only 5 power stations in the country that are capable of doing frequency control. Remember, no power system in the country, large power stations, can generate, start, stop, or change their output without getting a corresponding command or instruction from the system operators. The national people, system operators are the engineers who are operating at the national control centers. We call them system control center in our country. Other countries, we call them grid operators or system operators. They are the people who ask each and every power station to assign the specific power output that they have to generate. But there are 5 power stations, out of which 1 power station is allowed to operate without any corresponding instruction from system operators. That is the power station that is controlling the frequency. In our country, we usually use one of these power stations to do the frequency controlling, one at a time. So very quickly, if you, I will tell you how that is happening. Let's say out of these power stations, now let's say I have not shown you the load curve. I will later show you the load curve. let's say we are at a point like this in the load curve. The supply is equal to demand. Demand and generation are equal. Frequency at 50 hertz. Let's say, for example, at this time, the Kotelawala power station is doing the frequency controlling. Kotelawala has 367 megawatt units. So let's assume that one Kotelawala unit is doing the frequency controlling at this time, and it is loaded for 30 megawatts, right? It can have any load in between 0 and 67. So let's assume that it is at 30 megawatt. My system frequency is 50. So with time, when the consumer demand goes up like this, the demand side increases, generation is still not changed, so frequency can come down. As a result, this person, the Kotelawala operators, are now assigned to look after the frequency. So what he does is, he will change his power output again to a certain value and bring back the supply balance so that frequency is 50 hertz. So that is what is done by the frequency controlling power station. He will keep on always looking at the system frequency. He will adjust his output and always ensure that the frequency is maintained at 50 hertz. Then what is the role of the system control engineers? They don't have to do anything virtually because this person is taking care of the frequency. No, because if the frequency controlling power station reaches one of its limits, either its upper limit or the lower limit, he cannot keep on doing this exercise. Because now, for example, in this time, Kotelawala generator has only 7 megawatt margin to increase, but you are still in the increasing portion of the load curve. As a result, system operators always keep an eye on not only the system frequency, but also on the output of the power station that is doing the frequency controlling. And when they notice that the frequency controlling station has reached one of its limits, they will intervene and change the output of some other power station so that the frequency controlling station always come back to its mid region. For example, in this case, if the system operators increase the output from some other power station, I will later tell you how they decide this some other power station. But let's say they increase the output of, let's say, combined cycle power plant at Kalandrissa by 40 megawatts, right? So they notice that the Kotelawala had now come to this upper limit. They increase the output of the combined cycle plant by 40 megawatts. Then what happened to the frequencies? The generation side become heavier. Frequency goes up because now additional 40 megawatts have come to the system. Kotelawala frequency control engineer notices that, and what he does is he reduces his output by 40 megawatts, so that once again the system frequency will be 50 hertz, and Kotelawala frequency control machine is brought back to its mid region. So that is the activity that is happening day in, day out in the power system. There is a person to look after the frequency. And when that person's output comes to either the lower end or the higher end, system operators intervene and change the output of some other power station, right? Some other power station, and bring the frequency controlling station to somewhere at the middle of its capable output. So this third activity, the changing of this output by some other machine, we call it the economic dispatch. You will later once again learn this, because this is the first time that economics come into the picture. All these three activities are mainly technical. In real time, it is the kinetic energy that is doing the balance. In governors, once again, it is the generator governors that is doing it. Frequency control, once again, it's a technical thing based on engineering judgment, technical judgment. First time economics come into the picture using one of the machines that is already in operation, right? Already available unit, already connected unit to the system. They either increase the load or decrease the load in order to bring the frequency control station back to its mid region. This is called the economic dispatch. For system operators to perform economic dispatch, there must be machines already connected to the system. In other words, that means we have to, at one point of the time, we have to decide the machines that we need to connect to the system. which we call it the unit commitment, right? You will later learn this when you're doing power systems, how we do the economic dispatch. Economic dispatch is done using what we call the merit order. I will later show you the most latest merit order in the country. This is based on cost. Unit commitment is much more complicated exercise. Sometimes this is done even weeks in advance. So unit commitment, economic dispatch, frequency controlling, and governor are the main activities in the power system. And also to do unit commitment, there is another activity called operations planning. So I will touch very briefly about operation planning also to give you an idea about how we decide this unit commitment and economic dispatch, because this is very important. Our power system is one of the rare, very few power systems in the world which is having a very high proportion of hydrothermal mix. So we have to have a lot of coordination between the hydro system and thermal system, which I would very soon explain to you to give an idea about how this is done, the operation planning is done. Right. This part, I will not touch upon this part. This part belongs to planners, the type of job that I am doing, expansion planners. This part belongs to the operators. Right. So let's now I will take you to the second part of my lecture. I will give you an overview on the Sri Lankan power system and how it is operated. This is very interesting. Listen carefully, ask any questions at the end if you don't have any gray area, because as I told you before, this may be the first time and the last time that you will be hearing some of these things. I will first take you to the daily load curve of Sri Lanka. I'm sure you must have already seen this. This is an actual SCADA screenshot. SCADA is called System Control and Data Acquisition System. These are the monitoring systems that we use in power systems, not only power systems, in any engineering or control establishment. They are called SCADA, so Supervisory Control and Data Acquisition. These are the large monitors that you must have seen where system operators are watching. So this is actually actual load curve of Sri Lankan power system within a certain day. This is actual screenshot. This portion is 1 day. So I will very quickly explain this. You maybe already know. This is 0-100 hours of 12 midnight. And you know that our demand for electricity gradually comes down as the time goes and reaches a minimum at about 2 a.m. in the morning, or approximately between 2 a.m. and 3 a.m. it reaches a minimum value. And if the following day is a working day, right? This load curve is pertaining to a working day. After about 4:30 a.m., this started going up like this and reaches just before 6 a.m. around 5:50, 5:45, 5:50. Just before 6, it reaches what is called the morning peak. And though it takes about 2 hours for it to gradually reach the morning peak, the moment it reaches the morning peak, it comes down because this is due to sunrise. People all started switching off their lights. So that is why you see a peak like this. Then if the following day is a working day, again, people will go back to their factories, offices, the demand will go up. You will see a small dip here. This is, you will not believe me, this is the 10 a.m. tea time dip. You can still see this, you can notice this in your load curve. Then you go back again, reaches your lunch time, 12, your lunch time, again this will come back, gradually come down. After lunch, this will start going up. Once again, around 3, this reaches another small peak. Then thereafter, this started coming down again. After about 5, people go back home, coming down. And then when the sun sets, this again started going up like this, reaches what we call the night peak. Right? This is the highest point at which highest demand in Sri Lankan load curve right now. We call it the night peak. And once again, this remains about, unlike the morning peak, night peak remains for about 1 hour. Right? People, you watch your teledramas, news, everything, and it started gradually coming down and repeat almost same thing in the next day. So if you take one 24-hour period, next day is a repetition of this, except now, for example, if this is a holiday, this load curve shifts to the right-hand side. People sleep a little late, and even the morning peak is not so prominent. So it's less than this in a holiday. Of course, I have a very interesting collection of load curves with me during my 9-year period as system control. There are very interesting load curves. One load curve, I will share a story about. It was one particular load curve that I have with me. That load curve belongs to the day where I'm sure, I don't know how many of you were there at the time, the very first Cirrus Superstar reality program, right? It was somewhere in the middle of 2000, somewhere in 2000, I think 6, 7, I can't remember exactly the year. That was the very first Cirrus Superstar program. It was very popular, the very first reality program. The load curve was not like this. The load curve was something like this. The load demand was not dropping like this, but instead it was going at a tangent like this, right? Where I have the load curve going at a tangent like this. And when the event is over, you will see a almost 200 megawatt vertical drop. Almost 200 megawatt, almost vertical drop when the program was over. So there are some, I have an interesting collection of load curves pertaining to very special days. But my question to you is now, by now, you know that the supply is equal to demand during every point along this load curve. You know that in real time. My kinetic energy helped me with that. But very soon my governors intervene and still help me with maintaining the supply demand balance. But whatever it is, during every point along this load curve, supply is equal to demand. How is it then that we know that the Cirrus Superstar program is the first of its kind? How do the system operators know that the load is going to behave like this? Of course, it's not a very difficult thing. If you are an experienced system operator, they all know that if the load is not behaving the way that it normally behaves, but it behaving in a very different way, they remember, unlike any other person who is working in the country, system operators have a special privilege. They have a television set installed in the National Control Center maintained by CEB. So during my days at system control, that was in early 2000 up until about 2011, we were very fortunate to watch all the cricket matches that were shown on TV because we have a television set in the National Control Center, not as a privilege for us to give to, not as a perk, but what is shown on TV influences the demand. So system operators would know that. For example, even in this day, when this happened, I was the chief engineer heading the National Control Center. I was the chief engineer system operations. When that happened, still my staff knew that there's something strange going on. Since they have television, they know that this is due to this program. And they also know, they are experienced enough to know that if the demand is not dropping the way it normally does, once the program is over, it's going to drop like this. So they are experienced enough. So what they would normally do is they will keep the generating stations that are capable of ramping down to take the very fast ramping down operation that is required to match the demand of consumers. For example, if they shut down their generators in the normal merit order and keep the cheapest ones, right? That is how we operate the system. We shut down the most expensive one first. Even if during this day, if they keep shut down all the expensive ones, keep the cheap ones, of course, this particular time, the coal was not there. But let's say they had a coal power plant, the coal power plant will not be able to follow this 200 megawatt drop. It takes time. Coal steam technology takes time to change the output. So every point on the load curve, there must be technology, generating technology that is capable of following this load curve. That is why we mark the different regions of the load curve differently. This is what we call the base load, because our power system demand never drops below a certain value, certain minimum. This is now at about 1,200, 1,300. So during this load, we have to supply 24/7. So this is what we call the base load, for which we need to have base load power plants. Now, usually our base load is taken by coal. These days, we are experiencing a very wet weather. This is a record year for our system. This is the most wettest year on record. All our hydro reservoirs are spinning. So these days, hydro and coal are taking the base load. Not only the base load, what is on top of the base load, we call it the intermediate load, right? So this is called the intermediate load. base load is taken by large power plants that do not usually require to change the output that often. But intermediate load power plants are the power plants that require to change the output, but not as rapidly as the other power plants, which are called the peaking power plants. So these are the peaks that I was referring to earlier. This is called the morning peak. These, once again, don't worry about the numbers. These numbers change, right? For example, the highest peak is now about 2,800 megawatt. This is just an average value that I'm showing, just to give you an idea about what is the day peak and what is the night peak. So these are peak. We call them peak. These are intermediate. This is the base load, and we expect that in the middle of next decade, we expect that our peak demand, our system peak demand, would be the day peak, right? Our system demand. We expect our peak demand. There was a question in the chat. I will answer that as I go on. We expect that our system demand would be the day peak. All developed countries, system demand, actually the peak demand is day peak, not the night peak. But in Sri Lanka, it's still the night peak driven by lighting loads. The question in the chat is whether we can use Nava-Lakshipana machines for frequency controlling. We used to control frequency from Nava-Lakshipana for ages, but now there is a problem for the last, I think, 3, 4, 5 years. Nava-Lakshipana cannot do frequency controlling after there is a certain modification to their systems, but thereafter the machines are not capable of doing it, unfortunately. It's one of the, when I was at the system control, it's one of the preferred places where to do frequency controlling Nava-Lakshipana vertical turbine Francis machines, but not any longer after certain modifications done to the control system. It's not due to the control system, but due to some other modifications. So unfortunately, that feature is not there. Right. So let's move on. Slides have got stuck. I will stop sharing and I will come back. This sometimes can happen. I will stop the sharing and I'll come back. Right. Okay. Now it's working. Now let's see how this supply demand balancing act is done. Now I told you earlier, we have we have on one side we have the consumers, we have on the other side we have generators, and we have to match the change of demand from the consumer side with the generators. So on this side of the balance scale, Sri Lanka, we have these generators. We have about right now 1,400 megawatts of hydro at his control, and right now we have about 1,500 megawatts of CEB owned thermal power plants. And right now our IPP stands for independent power producers, or the private thermal power plant owners. The fleet had now come down to 433 megawatts. But we will soon add another 124 megawatts into this, because 2 expired contracts of Feasibility and Matra are going to be renewed. So this will increase. So all these are the generators that this system operator has on this side to be used to balance the changes that are taking place on this side. But I have not included to these figures another 800 megawatt plus non-conventional renewable energy. We call them other renewable energy or non-conventional renewable energy, NCRE. They're mainly consisting of mini hydro, wind and solar. We have about 800 megawatts. I have not included this figure. By this time you have figured out why, because they cannot be controlled. So they can, this system operator can only use the power plants that he has on its control, even though this wind is shown on this side. Wind plant is actually on this side, but that is not at his control, right? Normal conventional wind plants. This become a problem, because in a conventional power system, all this time, only the consumers are changing. The changing factors are on this side. It's only the consumer demand that is changing. and the system operator only has to adjust its conventional power plants to match the consumer demand. But now we have a much bigger problem. Even now, the generators on this side are also changing. The solar power is changing, wind power is changing, change due to the availability of resource. And as a result, system operation is getting more and more difficult. I will touch upon that as we go on later. So these 800 megawatt power, now this figure is getting increased by the day. We are now we have about 1000 megawatts of generators, solar, wind, and mini hydros. They cannot be controlled. One thing, they cannot be controlled due to their technical nature. Other thing is they are too small to be controlled. They are scattered. These mini hydro plants, we have about 420 megawatts of mini hydro of 1 megawatt, 2 megawatt size. It's not practically possible for him to control. Second, it's not proper for us to control because these power plants, whenever the resource is available, they will start generating. If we curtail them or if we ask them to stop generating, we will lose the resource. So as a result, they are not normally controlled. So this is how the system supply demand balancing act is done at a glance, at macro level, right? Remember, once again, another question: how do the system operators know that his consumer and his supply and demand is in balance? By looking at the frequency. He doesn't know that. He doesn't know whether his supply is equal to demand, but he keep an eye on the frequency. And when the frequency is falling, that means his consumers are demanding more, he's generating less. On the other hand, if the frequency is increasing, he knows that he's generating more, his consumers are demanding less. By now, you know that whatever is the balance, if we generate more or if we generate less, whatever is the balance is either stored in the kinetic energy or released by the kinetic energy. So actually, kinetic energy is helping him to maintain the real-time balance, and that is what is reflected by as a change in frequency. So I'm sure, even though you have not done any big theories by now, you can visualize what is happening in a power system up to that extent. So let's move on. This is once again, I'm come to a very interesting part: hydrothermal coordination. Let's now see how we coordinate the hydro system and thermal system in order to decide from which power plant we generate power. Before I take you to hydrothermal coordination, there are very important policies that a lot of people don't know. I will put them on the screen so that these policies are strictly adhered to when you're operating a power system. First policy is called the system operations priority order. For example, when you're operating power system, when you're doing dispatch, there is an order, of course. First is we have to think of safety of people. Second, protection of equipment. Third is the availability of supply. Fourth is the quality of supply. And the last comes economics. For example, I will tell you, if we need to trip off a generator, even if we have to trip off the large 900 megawatt coal power plant at Norachole, if we trip off the entire coal power plant, 3 into 300 megawatt coal power plant for its own protection, there will be an island-wide power failure most likely. But can we do that? Are we allowed to do that? If we do that, can we charge for doing something improper? No, because we can do that because protection of equipment comes at a higher priority than availability of supply, right? So there are again, I can give you many actual real life examples of how this order comes, but since I don't have time, I will not bother to explain. What you have to understand is rupees and cents comes at the very bottom. So a lot of people think we operate power system strictly based on the merit order of dispatch or based on cost. No, we have to take care of higher order priorities. For example, even if we have, sometimes we have to operate machines in order to maintain the voltage, sometimes even violating the merit order. But we can't do that because voltage is connected to the quality of supply. Sometimes even forgetting economics, we have to generate machines. You will later learn that voltage, by now you know that your active power is connected to frequency, megawatts is connected to frequency. You know how it is happening via kinetic energy, stored kinetic energy. Similarly, a system voltage is connected to reactive power. So sometimes we have to use generators to give reactive power. Sometimes we have to do this in violation of the merit order, but that is allowed because economics come at the bottom. The next most important operating policy priority order is when it comes to using water. Remember, you will later see that the water resources in this country are used not only by CEB, but by a lot of other stakeholders. We are controlling 6 out of the largest reservoirs in the country. Out of large 7 reservoirs, 6 largest reservoirs are controlled by CEB because water from those reservoirs are released through our hydro turbines. But still, we don't own the water resource. We have to share the water resources with other stakeholders whose water usage has a higher priority than power. You can see that power comes at the very bottom of this water utilization priority order. For example, first comes water service and drainage, which is drinking water. I will later, since I don't have time, but I will explain this. In 2019 April, we had to resort to power cuts. A lot of people think that that power cut was result of we not having water to generate power, but that power cut is more due to the fear of not having enough water at Castlereagh and Mousekale, which would result in a shortage of drinking water supply to Colombo. So I will, when I put those diagrams, I will explain more. So this comes at the top. Then environment means sometimes we have to release water from reservoirs due to environment reasons, like at Upper Kotelawala and Kotelawala. Third is irrigation, agriculture, right? Even though we don't have any water, we don't have any power, even though we have to resort to power cuts, still, if the agriculture sector say no, you have to release, you have to stop generating power from hydropower. We need that water during the agriculture season. We have to comply because that is a high priority. So even though we have hydropower stations, we have hydropower resources, even though we control 6 largest reservoirs out of the top 7, still we cannot release water the way we like. So keep this in mind, and we will later see how this is put into actual practice. So I will, in order to understand this more, I will take you through a small tour along the reservoir system or the power system, hydro system of the country. First, if I take all the water in all the hydropower reservoirs, put them into one single tank, one single reservoir, and if that one single reservoir is filled to the maximum capacity, that reservoir can hold about 1,250 gigawatt hour equivalent energy units. That means we measure water not in volume. We measure, of course, we measure in million cubic meters also, but we measure the water quantity stored in our reservoirs in terms of the energy units that it can generate, right? Then if we somebody is writing on my wall, can you please, so, why doing that? Right, okay. If we can put all these water into one single tank, and if all the reservoirs are full to the capacity, that reservoir, that tank can hold 1,250 gigawatt hours. A gigawatt hour is 1 million units. So if you put this into proper perspective, for example, these days all my hydro reservoirs are full. You may think that this water is sufficient to generate few months. No, not so. Every year you need about 16,000 gigawatt hours of electricity to generate. Out of that, even my total reservoir capacity can only store about 1,250. So how are we managing this 1,250 reservoir system? Every year from the skies, we get about annual inflow of 3,500 gigawatt hours. You can see that our total water holding capacity of all the reservoirs together combined is only 1,250 gigawatt hours. But from the skies, on average, we get about 3,500. Now this year, up to yesterday, we have got about 5,010 gigawatt hours. This year is going to be the wettest on record. We have last 100-year rainfall figures. This is going to be the wettest on record because we have never experienced this much of inflow because we still have about 1.5 months left. But normally the average inflow that you get is 3,500. The holding capacity is only 1,250. So as a result, what this means is that we have to generate about 3,500 every year. So this is not an easy task to do, managing a tank which has holding capacity of 1,250 while we are getting 3,500 from the sky. We have to generate 3,500 in order to either stop it from spilling or reaching the minimum operating level. So this is not easy. Also, this is even more difficult because in our country, if I put all the average inflows that we received from the period 1991 to 2018, this slide is old, but just to give an idea, these are the monthly inflows that we have received, daily average inflows monthly. So you can see that the first 3 months of the year are dry, but we get rainfall like this in a different pattern. So we are now in November, December, which are anyway wet months. So we are not getting them in a uniform manner. Also, even though I call this one single tank, even though I draw it as a one single tank, it is not one single tank. It is consisting of mainly six number of smaller tanks of different size, right? This denotes the 6 largest reservoirs. I have not included the smaller ones. So this my single tank, even managing a single tank is different of 1,250 megawatts, but managing that single tank is actually not a single tank, but it is consisting of 6 different chambers of 6 different sizes, and each of them are getting rain during different seasons because some of these reservoirs are getting during the northeast, some of them are getting during the southwest, some of them are getting during the intermonsoons, some of them are fed by both monsoons. So they are not getting their rainfall equally, they are from different periods, and the size of the power plants that are connected are also not the same. So managing a hydro system like this, though people think it's easy, it's very difficult. Even now, as I talk to you, almost all the large hydro reservoirs except Samanalawa is spilling. They're all spilling. Right. Now, this is how the storage in my tank had varied over the years. This is drawn up to yesterday. The red line denotes this year. This is the tank. This is in gigawatt hours. This is in the months of the year, January to December. This is, I told you, when it is full, you can generate about 1,200 gigawatt hours. So this is the maximum capacity. Now it had reached maximum capacity. That is why most of the reservoirs are spilling. This year is a very, very wet year, if not for which we would be having power cuts by now, because most of our long-term power plants that we expected have not come. Our capacity additions have not taken place as according to our plans. We are running at a capacity shortage, but thanks to this very high inflow that we are managing, and also thanks to COVID. Because of the COVID, there is a reduction to demand, and also because of the very high inflow, we are very happy, we are very lucky to have very high inflows to our hydro reservoir. So hydro system is running at full capacity. Not so much in other years. Look at this curve. This is 2019, a power cut year. I told you somewhere here in March, April, we had to resort to load shedding. Not actually because we thought this would reach minimum operating level. Normally, if this curve, any of the curves touch 200 mark, that is definite power cuts. Right? We cannot allow it to go beyond 200 gigawatt hour storage mark. We have to resort to power cuts. 2019, we started power cuts even earlier than that. It is not because of course, we were worried about electricity supply, but it is due to some other reason. Drinking water, I will explain that a little bit later. So this is how the reservoir storage, the total reservoir storage had behaved over the years, year by year. But right now we are here somewhere here. So hopefully we can end the year with a very high storage, which is very good for the next year. But even though we start with very good storages, you can see even in 2019, we started with a very high storage, but the northeast monsoon failed. So quite often the southwest monsoon failed. So sometimes the weather patterns have become very erratic. Sometimes usually we miss the southwest monsoon. Southwest monsoon comes somewhere here, and you get more rain from the northeast. Northeast somewhere here. These are northeast intermonsoon period. But usually we sometimes have a tendency of missing one monsoon, right? Now I will take you through a very quick tour around the three main reservoir systems of the country, so that you can get a better idea of the hydro system. I will first take you to the Mahaveli system, right? This is the Mahaveli system, all the reservoirs. Let me start from the top. You all know that this is the Mahaveli Ganga. You all know that the largest tributary of Mahaveli Ganga is Kotelawala. So across Kotelawala, there are two reservoirs, one large reservoir, the Kotelawala reservoir, and one small reservoir, Upper Kotelawala reservoir. So how they operate is, for example, when we store water at the Kotelawala reservoir, and when we generate power using the Kotelawala power station, these squares represent power stations, these represent reservoirs. So when we generate power from the Kotelawala power station, once again water is released back to Mahaveli Ganga, right? And that water comes to a place called Polgola, where Polgola there is a very small pond, very small size. We don't call them reservoirs, we call them ponds. At Polgola, something very strange happened. There is a diversion. Polgola is a diversion where if the Mahaveli Ganga is allowed to flow the normal way, it would have flown this way, right? But at Polgola, there's a diversion from Polgola along a long underground tunnel. Water can be taken to Ukwela power station, and when Ukwela power station generates power, it can get Mahaveli water along this into this side. This is a interbasin transfer of water. When Ukwela power station generates, it releases water to Suduganga, whereas water could have flown this way. But Ukwela diversion, it channels water to Suduganga. It's a different basin. And along Suduganga, water goes to Bovatana reservoir. And when Bovatana generates, it is released to Ambanganga system. And once again, it will join Mahaveli Ganga somewhere down here. Why we do that? Because there is a very large agriculture settlement, Mahaveli H and Mahaveli D on this side. To take water to these Mahaveli farmers, we divert water from Polgola, generate Ukwela, put it to Bovatana, and either to Bovatana power station, you have the Angamadilla Anikat somewhere here that is supplying Parakram Samudra. It's not drawn here, shown here. Now we have another reservoir here, Morgahakanda. Or along Bovatana, there's another canal where the flow is along gravity. It's called a KH canal, Kalave canal, to supply these farmlands. Or if water is allowed to spill over the Polgola reservoir, water will reach Victoria reservoir, very large reservoir. These are not drawn to scale. This is a very large reservoir. And when Victoria power station generates, that water is again released back to Mahaveli Ganga and will reach the Ramdenigala reservoir. And when Ramdenigala reservoir generates 120 megawatt power plant, once again water is released to the Mahaveli Ganga and it will reach the Rantambe reservoir. And from Rantambe is actually again another small pond. It's 21 MCM. MCM stands for million cubic meters. When Rantambe generates, water is once again released back along the Mahaveli Ganga and it goes this way. Again, there is a large agricultural settlement, Mahaveli A, B, C, and E systems. So what you have to understand is, if you are a system operator, if you are in the desk of in the National Control Center, controlling the system, You can generate from any of these power plants. They're all at your control. It's a matter of lifting the system forward and asking these power stations to start and generate. Nobody will prevent you. They will start, they will obey your command and they will generate. But can we do that is my question. Now, if you're a system operator, I will ask you the question, where do you like the water coming from this side to go? Do you like it to go divert to Ukwela, or do you like it to go downwards to Victoria? I am sure all of you would say you like to go it downwards because this is a small power station of 36 megawatts. This is again another small power station of 40 megawatts. Whereas Victoria is 71 megawatt into 3, Randanigala is 60 into 3, 120, runtime is 50 megawatts. You have very large megawatts can be obtained if water is allowed to go this way. Not only megawatts, for example, if you send 1 cubic of water this way, 1 cubic of water this way up to Victoria, that water contains 2.5 times more electrical units than if you send the same water, same 1 cubic meter along this way. 1 cubic meter of water this way has 2.5 times more energy, electricity, than if you allow it to go this way. Remember, we are talking in million cubic meters, not just 1 cubic meter, million cubic meters. But can we do that? If you are a system operator, if you are in the National Control Center operating the system, can you decide whether you want water to go this way or water to go down? No, you cannot decide because power comes at the very bottom of water utilization priority order. For example, we have 2 cultivating seasons, Maha and Yala and Maha. Maha is based on rainwater. Yala is based on stored water. And the main storage that all these farmers have before their Yala cultivation is Kotelawala. Because all other reservoirs that they have very large network of irrigation tanks. They are much smaller in size in comparison to our irrigation reservoirs, our hydropower reservoirs. I will later show you a diagram showing the storage capacities of irrigation reservoirs and hydropower reservoirs. You will see that, that is why I told you, out of the 7 largest reservoirs, 6 reservoirs water is released through hydro turbines. They are in the control of CEB. But still we cannot generate as we want from these reservoirs because our water utilization comes at the very bottom of the water utilization priority order. So how this is done, how we decide whether to send water this way or this way, I will later tell you. What I have, the idea that I like to get you is that, for example, just before a Yala cultivating season, if I put all the water, I empty Kotelawala reservoir and strengthen these reservoirs, I fill these reservoirs, there will be a social issue. There will be social issue. These farmers will not be able to cultivate during Yala. There will be unrest. So we cannot do that. We have to use water very taking into consideration their individual requirements. So these are of course, these are the capacities of reservoirs. You can see that these are very large reservoirs. These are MCM is million cubic meters. Upper Kotelawala is very small. Runtime is also relatively small. Polgola is extremely small. Right. Then these are the sizes of reservoirs in the country. This is a million cubic meters. This is, of course, is from a small newspaper. It's not of good quality. The largest reservoir in the country, if somebody asks you a question, is Ceylon Electricity Reservoir, almost 950 MCM. The water from ENG.Lakshitha power station is released through ENG.Lakshitha power station. So we control that water. Second largest reservoir in the country is Randanigala. We control that water. Third largest reservoir in the country is Victoria. We control that water. Fourth largest is Madhuruvaya. Of course, there is no power station there, so we don't control that water. Fifth largest is Samanalavavu. We control that water. Sixth largest is Udavallave. We control that water. Seventh largest is Kotelawala. We control the water. So all these water in these power stations, these reservoirs are controlled by electrical engineers manning the National Control Center. but still we cannot generate or we cannot use the water the way we like, because we have to share them with other stakeholders. I will tell you how you do that. A lot of people, when I ask this question from live audience, what is the largest reservoir? They usually say Parakramasamudra. Parakramasamudra is somewhere here. Even Samanarayava is 2.5 times larger than Parakramasamudra. So these are irrigation tanks that we have. They are quite small in size compared to our large hydro reservoirs. Right. Then come to Lakshapana complex. Lakshapana complex has a different constraint when you're operating the power system, hydro system. The Lakshapana complex is different. I will first give you the sizes of these reservoirs and then I will explain. Lakshapana complex is built at the confluence of two rivers, Muskelioya and Kehelgamoya. Across Kehelgamoya, we have built Castle Reservoir. Across Muskelioya, we have built the Mausukale Reservoir. These are the two large reservoirs. And when we generate power from Mausukale Reservoir using Canyon Power Station, we release it to Canyon Pond. These are quite small in comparison. We call them ponds. On this side, when we generate the Norton Power Station, Vimala Surendra Power Station, we take water from Castlereagh and put it to Norton Pond. And when the old Lakshapana Power Station generated, the first hydro power station built by the great engineer Vimala Surendra, DJ Vimala Surendra, old Lakshapana, we take water from Norton and put it to Lakshapana Pond. On this side, we take water from the Canyon Power Station using Navalakshapana Power Station, release again back to Lakshapana. From the Lakshapana Pond, we have the Polpitiya Power Station. We take water and release back to Kalanigangar. There is another power station coming down here, Broadlands. 2 days back, we started filling the intake tunnel of Polpitiya Broadlands Power Station. You will see it start generating power very soon. So that's that is Broadland Power Station. Now in Lakshapana complex, there are no downstream irrigation requirements or agriculture requirements along Kalanigangar. There are two other different constraints in the when you operate in the Lakshapana complex. They are called pond balancing, right? This is a cascade of power stations. What is pond balancing is, I will very quickly explain. These green cages that I have shown you are the amount of water that you release when you're generating 1 megawatt. Of course, this CFS refers to cubic feet per second, because still in Lakshapana complex, still we work with cubic feet. We don't work with cubic meters. So apologies for that. But these are the water rates. This is the amount of water that we release from each of these power stations when we generate 1 megawatt. So if you're smart enough, you can guess what is the power station out of these 5 power stations. What is the power station with the highest head? Head is the elevation difference between the reservoir and the hydropower station. We call it the head. So if you are smart enough, you will guess from these water quantities, the water rates, that Navalakshapana has the highest head, because it can generate a megawatt by only releasing 8 cubic feet per second. Whereas to generate 1 megawatt from Canyon Power Station requires 3 times that water. The problem with the Lakshapana complex is that if you calculate, if all these power stations are running at full capacity, if you concentrate on the Lakshapana pond, if you calculate, you will see that if all these 3 power stations are running in full, if you take a small calculator and calculate, you will see that what is coming into the Lakshapana pond is more than what is going out of Lakshapana pond from Polpitiya Power Station. So in other words, when you run all these 3 power stations in full capacity, Lakshapana pond will go up. That means, but this is a very small pond, only 0.2 MCM. So what it means is that when we generate, if we want to generate all these 3 power stations in full capacity, for example, during night peak time, we need all our power stations at hand. Before night peak, I have to keep the Lakshapana pond level at a lower level, so that if I keep the Lakshapana pond at a lower level at about 6 p.m., when the night peak starts, I generate all these 3 power plants, and the Lakshapana level will gradually go up. And after about 10:30 p.m., this will reach at the top. Thereafter, I have to again balance out these three generators so that Lakshapana pond level gradually comes down, because for the next day morning peak, once again, I need all these three generators. So before night peak, I have to lower the Lakshapana pond. After night peak, Lakshapana pond level will be at highest level. After night peak and before the next day morning peak, once again, I have to gradually bring the Lakshapana pond back to low minimum level or lower level. So these are called pond balancing. Same with all these ponds. When you're operating a hydro cascade like this, cascade means one power station releases water to the other power station, pond or reservoir, we have to do what is called pond balancing. This is not easy. So it means all these things, after looking at all other things, when you have pond balancing is not easy. There is another very interesting constraint in operating Lakshapana complex. I will explain that to you also. Sometimes, now remember I told you in 2019, April, we have to resort to power cuts because, not because of a shortage of electricity, but because of an impending water crisis in Colombo. Because this is the Kalaniganga system, this is Kalaniganga. It is Kalaniganga that supplies water, drinking water requirement to Colombo, and only upstream storage available in the Kalaniganga are Kasarle and Moskale reservoirs. There are no other upstream storages. So unless we keep enough water in these reservoirs, we would not be able to maintain a continuous supply along Kalaniganga, so that the Colombo drinking water supply is ensured. In 2019 April, what happened was, we forecasted that if we start generating at that level, Kasarle reservoir is to reach minimum operating level within 2 weeks. Moskale reservoir is to reach minimum operating level within about 3 weeks. That's very dangerous. Colombo will not have drinking water. As a result, even though we had capacity in the reservoirs to generate electricity, we have to curtail supply, curtail generation from Lakshapana, cut your supply and get the blame. Not because we don't have enough ways of generating power, but because we have to conserve water for the water supply board. So should we do that? Yes, because that is coming at a higher priority. I will tell you another very interesting example. Sometimes during very dry period, at Ambatale intake is further down Kalaniganga near Colombo, where it supplies water to Colombo. Sometimes there is a salinity intrusion. That means water is coming back from the seaside into the Ambatale intake during dry periods. So during dry periods, we are also operating our power system very difficult because our reservoir levels are also low. During such times, usually the water board makes a request from us and say, please increase your generation from Lakshapana complex, because we want to flush out seawater. We want to prevent seawater coming into the Ambatale intake. So when a request came from water board to CEB asking to increase generation from Lakshapana complex, at a time our reservoir levels are also very low and we are managing our reservoir also with a lot of difficulty, what do you think we should do? Should I tell them that you have to mind your own business? We have built these reservoirs out of our own money. They have to generate power as and when we require. So if you want to prevent seawater coming from the Ambatale intake, you have to take another precautionary measure like putting a salinity barrier. Don't ask us. We generate power from Lakshapana the way we want. No, we cannot do that, because as per the system priority order, drinking water comes at the top. So what in times like this, what we do is, again, that is very interesting. Normally, this seawater intrusion comes during high tide. So usually these high tides come quite late at night. So what we normally do is, for example, if we get tidal chance from the Met Department. Met Department has tidal chance because high tide and low tide are due to lunar activities. So we know, they know exactly what is the time you get high tide and what is the time you get low tide. So we borrow these tidal charts from the Met Department. And for example, if there is a high tide due in 2 a.m. in the morning, now we have to release water from Lakshapana complex by generating Polpitiya power station, so that that water reaches Ambatale intake before 2 a.m. before the high tide. So you may think that it's quite easy. If you want the water to reach Ambatale intake at 2 a.m., we can start generating Polpitiya power station at 1:30 a.m. No, the water traveling time from Polpitiya to Ambatale is 10 hours. So if you want to have water at Ambatale at 2 a.m., we have to generate power from Lakshapana complex 10 hours ahead. While doing all these balancing acts and while preparing these ponds to prepare for the night peak, we have to do all that. So that is very difficult, but that is very interesting challenge. But operating a hydropower system, hydropower network is not so easy and straightforward that a lot of people think it is. Let me, even though I presented to you that schematic of Mahavali, that is not exactly the way Mahavali reservoirs are situated, but I will not go into detail. The next one is Samanalvaeva. Third, this is the second tallest dam and the second longest dam in the country, the third largest reservoir, rather fifth largest reservoir in the country. There again, this has a different constraint because Samanalvaeva is built at the confluence of Valave and Biliholoe. It's a large reservoir, and when water is taken to the Samanalvaeva power station and when water is released back to the Valave river, there is a portion where the normal water is blocked. We have taken water, we have blocked, put up a dam, taken water, released back, but in between there is a very large agriculture settlement called Kaltapa. So they need water. Of course, you know that Samanalvaeva has a leak. It's not from the dam, it's from bank, it's right bank. This leaking water is sometimes not enough for Kaltapa farmers. So at those times, what we do is we have to open out irrigation outlets and release additional water from the Samanalvaeva reservoir to Kaltapa farmlands without generating power. This costs millions of rupees of losses to CEB because we are releasing water simply without generating power. But can we refuse? We cannot, because agriculture coming in at a high priority. So this once again is also another, we have to do that. So let's now see how this is done, how the sharing of hydro resources with others, what is the methodology? I will very quickly tell you in order to give you enough time to ask questions. I'm sure you must have asked a lot of questions. Remember, this presentation, even when I do it to full CEB audience, I usually do it to CEB engineers. Even after one full day, they always make the comment that time is not enough. You have to have more time. So there is no end to this presentation. That is why I told you, this is a very broad subject. This is a very interesting subject. I can go on talking for one full day, but I will try to share with you the maximum that I can do today, because this is a very broad subject area covering the whole spectrum of how the power system is operated and managed. So I will now very quickly tell you how the water resources in the country are centrally managed. This is called integrated water resource management process in the country. This is a very well established process in the country. The person, the body, the agency that owns water resources in the country is not CEB. It's the Water Management Secretariat, we call it WMS, coming under Mahavali Authority. They have the statutory ownership of water resources. So they prepare what we call seasonal operating plans. We get involved in preparing seasonal operating plans. We have 2 cultivating seasons, Yala and Maha. For each cultivating season, we have a plan prepared. I don't have time to go into detail. And thereafter, this plan is monitored every week. At Friday, every week, there is a water panel meeting. There's a panel represented by engineers from CEB, Irrigation Department, Water Board, and Mahavali Authority, where they decide how much of water will be required in the next week. So week by week, the water resources of the country are managed within this broader seasonal operating plan prepared at the beginning of a cultivating season, taking into consideration the amount of storage at that time, taking into consideration the generation requirements, taking into consideration any large power plant outputs. All these are considered in devising the seasonal operating plan, and that is monitored and revised, and it's followed every week. So at water management meetings, they decide how much of water should be released from each reservoir in the following week, and that is released to CEB as a directive. They are binding to follow this. This is called water management directive. It is based on this directive that system control plans its hydro generation in the next week. So I will very quickly, I will not take time, I will very quickly take you through an actual water management directive minute. This is pertaining to somewhere in March this year. For example, I will not go into rest of the details. For example, you can see this particular week, they allowed us to operate Victoria at our requirement, because Victoria, even though we operate Victoria, that water can be stored at Ramdanigal. So I will not go into detail, just concentrate on these two. They want us to release 50 cubic feet per second of water during next week from both end. And the interesting part is, they said this is equal to 11 megawatt only 1 hour per day. Bovatana is a 40 megawatt machine. Even though we have a 40 megawatt machine, Bovatana, they say the water management directive say, no, you can't operate at 40. You can only operate at 11 megawatt. That is also 1 hour a day, right? That is the sort of constraints that we have in operating a hydro system. Not only that, the interesting part is, they also say, while doing that, you have to maintain the Bovatana reservoir at 249 meters above sea level. We measure all reservoirs from sea level, above sea level. They say you can generate not only at 11, you have to maintain, you have to ensure that you always maintain the Bovatana level at 249. Why? If I take your attention to Bovatana, this is Mahaveliganga, this is Kotelawala, this is Kotelawala power station. When Kotelawala generates, it comes to Polgolla. Along Polgolla, Suluganga, when Ukwila generate, water comes to Bovatana. Why they want us to maintain the reservoir at 249 meters? Because there is another canal called the Cage Canal, where the water flow is depending on gravity. So if we have a higher elevation, there's more water. So they want us to control water. So when we want to generate while maintaining water, the only option is, when we generate, we have to put back the water that is going out of turbines from this side. So if that means, in other words, when Bovatana generate, we have to also generate Ukwil. For Ukwil to generate, water must come from Polgolla. That means, for example, if we generate Bovatana at 7 p.m., we have to ensure that water, there's a water traveling time of 5 hours from Polgolla to Bovatana. If we are to have water at Polgolla, water must come from Kotelawala, unless there is site flow along Mahaveliganga, water must come from Kotelawala. And if you have to generate both, then you have to generate Ukwila 5 hours before. And also, if you have to have water at Kotelawala, you have to generate water at Polgolla, you have to generate Kotelawala 8 hours before. That is the water traveling time. So when one power station generates, we have to have a very coordinated planning in order to operate the power system, taking even water traveling time into consideration. That is the difficulty of operating hydro system. So this is actual operation of hydro power stations throughout 2019. This is the megawatt. The total installed capacity of hydro power station is 1,400 megawatts. This is day by day how the maximum hydro power that is generated. You can see that only during very small portions of 2019 that we have utilized the full 1,400 megawatt. This is the dry period of the year. Why we have generated very high capacity from hydropower? Because that is the cultivating season. This is just this is before, this is after this is somewhere Yala is somewhere here, and thereafter we store water. So we stop generating and we store water. Then after northeast intermonsoon, we again start generating power. So this is how it is. Even though on paper you have 1,400 megawatts of hydropower, we cannot use those resources the way we want. Every week, how much of water that we can release, how much of power that can be generated, decided after taking into consideration the requirements of other stakeholders. Right. Now, how about the thermals? Right. So we will very quickly say thermals. Thermals is fairly straightforward, but in thermal plants, there are two main types of costs. There are rather three main types of costs. You will later learn this when you're learning economic operation of generators. There are special theories you will learn. Thermal plants have two main types of costs. One is the energy cost. This is a variable cost, mainly fuel cost. The cost to generate a unit. The merit order is based on this cost, rupees per kWh. There is another cost, this is called start-stop cost. When we start a machine that is in standstill, just to start, sometimes we have to, it costs about millions, 4-5 millions. That is called start-stop cost. That is only incurred at the time of starting up. So that is normally not used in normal day-to-day economic dispatch, but only at a unit commitment at the startup. There is a third cost. You have to very carefully understand. This is called the capacity payment. That is not used by system operators for any of its decisions. This is again something very confusing. So that is why I am stressing on this. Now we have certain private power plants in our system. Whether it be a private power plant or CB power plant, let's take a private power plant, for example, a private thermal power plant. The business model that we have in the country is such that when a private power plant gives its power plant connected to the system and allow us to operate the power plant the way we want, the payment back to him for his investment, his return on investment, his profits, and his fixed costs are all paid via a capacity payment, which comes to billions of rupees per year. But this, all his profits are based on this capacity payment, and the capacity payment is not depending on whether he generates electricity or not, but it depends on whether he is available to generate electricity or not, because it is us who decide whether he generates. So it's unfair by him to tie up its profits to the amount of electricity units generated. As a result, all what he invested, all his profits, all his fixed costs are paid back to him via a capacity payment, which is billions of rupees per year. But in operating, the energy cost is a pass-through cost. It's a fuel cost. When we generate more, we pay energy cost. When we don't generate, we don't pay. So in operating a system, this capacity payment is not considered. A lot of people don't understand this. They said we should, but we should not, because it is called a sunk cost. Whether we generate or not, we have to pay the capacity cost. So there's no point in taking that into consideration to take the decision whether we generate or not. So, okay, this slide, this is the actual energy cost, the variable cost for this month. You can see that Lakvijay coal plant can generate a unit at 11 rupees and 40 cents. These are furnace oil based power plants coming in at 17, 18 rupees. This is the disputed West Coast power plant that you now should be know by now. We also call it Yugadharavi. Then Sapukaskanda heavy fuel. Then the diesels, combined cycle diesels coming in the range of 20s. When we go down, these are CB owned emergency plants, auto diesel, run on auto diesel. These are the gas turbines. Calendar is a GT7 gas turbine, 34 rupees a unit. Calendar is the frame 5 small gas turbines. They are quite old now. They should have been retired long time back. Costs of 50 rupees a unit. So these are the actual costs of generating power. If you ask me what is the selling price is about 16 rupees and 70 cents. But remember, this is only the variable cost. We have a lot of very high fixed costs involved in the system. I don't have time to go into detail. So you just want to see the difference between generating a unit from coal. Now this is after coal prices are now very high. International coal prices have gone up. As a result, it's 11, but this was hanging around 6 rupees, 7 rupees few months back. But now even the coal prices have gone up. Right. Then I will skip this slide. I will very quickly explain the transmission network on the country. Right. What you see on the purple color is the 220 kV network. What you see on the green color is the 132 kV network. In the future, we expect to have 400 kV at the transmission voltage because we expect a lot of renewable energy coming from this side. But I will not go into detail. I don't have time to, because I want to give you enough time to ask questions. So I will not take much of time to explain the transmission network. You have the Mahavali Reservoir somewhere here, Victoria, Port Malay, and you have the Mana wind is now evacuated through this slide. Your load centers are here. We have another 220 kV line now almost reached Hambantota. It's not marked in this diagram, but I will not explain to you this network. Later on, you will also have 400 kV backbone line included into this transmission network in the future. Excuse me. So very quickly, I will take you now to the future power system in a few minutes before I open out for your question. Before I tell you what the future power system is, you have to understand the CEB's plans. CEB has a long-term plans. We have two major long-term plans. We have the long-term generation expansion plan. I'm sure you must have heard about this. And we have the long-term transmission development plan. This long-term generation plan is prepared for a 20-year period, once in every 2 years. Transmission development plan is prepared for a 10-year period. During the planning process to prepare the long-term generation plan, we also do and prepare another plan. Actually, we call it a study called Renewable Energy Integration Study. So they go hand in hand. These two, now we have just started this process for the next planning cycle because government had given us a renewed renewable energy target to reach 70% of renewables by 2030. So that's a government policy that we have to comply. We cannot complain. But during its initial stages, when it was under discussion, whether what should be the proper policy target for 2030, we gave our inputs. We said it's not possible. It's not. We should go for a lower target. But now that the government had issued the policy, yes, we have to follow the policy. So we are binding on following the policy. We have started planning studies. All these three my planning teams are now working on preparing these plans. The importance of renewable energy integration plan is, now remember, these are the last 4 generation plans that we have prepared. All these documents are in the web. This is the latest generation plan. You may ask why we prepare plan in once in 2 years, whether we abandon one plan and completely do a new plan. No, when we go from one plan to the other, the committed power plants are kept and the remaining power plants, we do an optimization. Normally, the planning methodology so far has been, now remember when we are planning, we have to balance 3 aspects. We have to balance economy of supply, reliability of supply and sustainability, the green quadrant. When all this time, when we are doing planning, our philosophy has been to build the firm capacity. Firm capacity, the capacity that don't change the output the conventional power plants. And on top of this, we absorb the non-conventional renewable energies into this. Since we have the firm capacity base, all this time, once we first build this firm capacity base and add on top of it to supplement the firm capacity, the non-conventional renewable energy, the mini hydro, wind and solar. But now it had changed since 2019 because now earlier the renewable energy integration studies decided the amount of renewable energy that we could absorb to the system. This is a very complicated, complex study. It is the outcome of this RE integration study, the amount of renewable energy. But now the government policy forces us, they tell us the amount of renewable energy. So now the purpose of RE integration studies is to decide the impact of those renewables and how best to absorb the renewables and other interventions that we require in order to eliminate the adverse effects. So that is the current planning philosophies that we have inverted. It's completely changed now. I will take this slide and thereafter I'll stop, though there are some more slides left. I like to have a look at the bigger picture. This is the future that we want to take the sector gradually. If I take a timeline like this, on the right hand side, I am marked 2050. This is beyond my 20-year planning cycle, but the government had intentions to reach carbon neutrality by 2050. We are now here in 2021. Let's call it somewhat high carbon system, but still our electricity, the amount of carbon CO2 emissions in 1 kWh is still very low by the world standard. But let's call it the high carbon system, mainly oil and coal dominated in 2021. How are we planning to gradually take our country to carbon neutrality by 2050? The self-reliant indigenous system with self-reliant indigenous energy. Our plan is initially to go via a blue transition. The blue transition is gradually from coal to liquid natural gas. This is our plan. This was our plan. Now we have to change this somewhat, but you have to understand the bigger picture. We were initially planning to use LNG as a transition fuel, gradually transfer thermals from mainly immediately oil to LNG and gradually from coal to LNG. Even our own plants have stopped generating from coal after 2030. Now the government said you cannot generate any power plant from coal. So now in the next planning cycle, we have to abandon all coal power plants. But even in our own plants, we stop all coal power development after 2030 because we very clearly see that the future belongs to the renewables. But we have to go there gradually. That is the only problem. There's nobody disputing that future belongs to renewables. But we have to go there gradually. So our plan was to go there gradually via a blue transition in successive generation plans. A lot of people think that in one single generation plan, which is prepared for a 20-year period, we can take this leap, we can take the jump. We can't do that because some of the technologies are still emerging. So that is why we prepare generation plans once in every 2 years. So our plan is to, in every successive generation plan, take an aim at this direction. That was how we were doing. Our macro picture, the bigger picture that we were taking the country was in this line. The transition from gray to green is from successive generation plans. The important middle period is very important. We have to first make our system zero carbon ready. It's not about simply taking a jump from brown to green, but our system has to be ready. Because I told you at the very beginning, we have inherited synchronous power grids from the days of Thomas Alva Edison's and Nikola Tesla's. We have, in the day people decided that power should be transmitted using AC and not DC, you can Google the word war of currents. You know, there's a big debate during initial days whether you should have DC or whether you should have AC. Finally, AC won. From those days onward, we inherited synchronous power systems, and synchronous power systems has a limitation of absorbing non-synchronous technologies like solar and wind. So we have to make the grid ready for this transition. So our plan is during this middle portion to make the grid ready and gradually abandon the blue LNG and go for green. So that is why we have stopped developing coal power, not because it is cheap. Coal is still the cheapest. Don't have any doubts on that. Coal is the cheapest form of thermal power generation, leaving aside nuclear. But still, that is why still countries are using coal. But it is the coal technology, coal steam technology does not complement with renewables. We can't operate alongside renewables because you can't change the power plants. So our plan is to develop grid support technologies in the middle portion and gradually abandon LNG, stop building LNG power plants and transfer LNG into green, and even stop building LNG power plants somewhere here. And by this time, we hope the renewable technology will be quite matured, storage technologies will be quite matured. So that is why we wanted to have a gradual transition. And finally, all will be based on renewables. So that is the plan that we were taking the country. This was our previous plan. You can see that even to go, this is to aiming at 50% renewable. You can see that from 2020, this is the past, this is actual, these are major hydro. This blue portion is mini hydro, green is wind, this or yellow is solar. These are actuals. Even to go for 50% renewable energy, we have to go for a fairly big jump. This is what we were planning, but now the government say no, go for 70%. So you have to take this jump. So this is extremely challenging. This, even though it is the engineering challenge can be overcome, the implementational challenge and the financial challenge is enormous for the country. That is why when we engineers say something is yes possible, it should both be possible technically and practically. So we have a big question whether we would be able to achieve this, but still we have to aim for it because that is the government policy. So this is the direction that we are heading. These are the capacities we have briefly lined up to reach this 2030 magic figure of 70% from energy. This is the capacities. I will not go into detail, but just I will draw your attention to few figures. The peak power demand in 2030 would be 4,500. We would be having renewables of 7,500, out of which we would have solar and wind 6,000 megawatts. We expect a lot of excess generation in the system in the middle portion. A lot of excess generation, excess power generation. We call it the sunny Sunday effect, particularly during August, September, when the wind season is over, when the sun comes out, rain season is no more. During Sundays, why we call it the sunny Sunday effect? During Sundays, system demand is low. In a sunny Sunday where the sun is shining, we expect about 1,000 megawatts of more solar in the system than what the consumers are demanding. So we can do two things. We can curtail generation, but now we cannot do that because we need that energy. The only other option is to store them. How we are going to store? Now it is something like this. This person requires 10 units of electricity per day, but that 10 unit is now coming within 1/3 of the day because solar is generating only during this portion. So as a result, my system balance will be very difficult. And also when we rely on solar to give the supply to meet this 10 kilowatt hours, he will not have supply during night time. So we have to have storage. So again, when you're generating solar, this is a perfect solar day. When these pre-monsoon clouds are passing over, you will have it like this. All these changes, we have to balance out with conventional power plants. Same with wind. So what are our solutions? We are going to use pump storage hydrosis in the plant. We are now carrying out a feasibility study, which we very quickly want to extend into a project. We have two earmarked sites. I don't have time to go into detail. What pump hydro storage do is, you will later learn when you do energy systems. They pump water during the time that you have excess solar power, and during night time when the upper reservoir is full, they use that water to generate power during night time, and during daytime when the solar is more, it pumps back water. So that is how pump storage hydropower plants operate. There are few slides that I have, but unfortunately, since I need to give more time for you to ask questions, I will stop from these because I can go on and on. This is, I told you, it's a very broad subject, very interesting subject. There is no end to this, but I will take up your questions and I will take you through your questions to fill up anything that I have not shown. So with that, I will hand back the controls to the moderator and Ashan. You can take off from this and open up the floor for questions. I will also check the questions in the chat. I will stop from here because there is no point in continuing. There's so much to talk, and take up questions from now onwards. So I will hand back to the moderators for the time being.
Can I make a comment before you answer your questions?
Sure, sir. Please go ahead.
So this is one of the clearest lectures, technical lectures that I've heard. So thank you very much. I learned a lot. Some of the things like the traveling time of the water, I never realized that it is so many hours. So things like that. very important. I'll just make one more comment. 50 years ago, when I was in Manchester, I heard that they were looking at the football playing times, and especially the halftime. But at halftime, everyone goes and switches on their kettles and everything else, and the power suddenly shoots up. So today, you also explained that we are also doing something similar. Thank you.
Thank you very much, sir. Your comment is most welcome, and especially from a lecturer who is much respected lecturer, it means a lot to me. Thank you very much for the comment. I will take few questions on the chat, and at the same time, I will open out the floor for questions.
Thank you, sir, for the thought-provoking and interesting lecture. Now it's time for the Q&A session. If you have any questions, please unmute yourself and ask.
Can I first take the questions on the chat first, and then I will open out?
Yes, sir. Sure.
There is a question about why Navalakshapan is not used for frequency controlling. I explained that. And there is another question, how much of solar is required to reach 70%? Good question. As per the current estimates, I think is about 3,000 megawatts, approximately 3,000 megawatts of solar, and about 1,000 megawatt of wind is required to reach 70%. That is still we are carrying out the renewable energy integration studies. So still details are not over, but still we have lined up the projects because we have to develop the transmission network. So we have to raise finance. As a result, it's a rough estimate. I have shown it in a slide, but approximately about 3,000 megawatts. I will share this slide with you so that you will have the actual figures. Again, there's another question, why we are using 11 kV. Of course, 11 kV is a distribution voltage. Now we are gradually transferring to 33 kV because 11 kV has higher losses. It's a 33 kV kilovolt and 11 kV are distribution voltages. The question is why we use 11 kV. I don't know what the question means by why, because why instead of what? Because we cannot we cannot distribute using 230 volts because of high losses, and also we have to have very high conductor cross section in order to carry that power. Not only in terms of losses, but you will later learn from your power systems that there's a limit to which you can push power along a cable due to other limits. We call it power stability limit. You will later learn something called very interesting thing called P delta curve, where even if you have a conductor, still there is a limit to the power that you can push along that conductor, right? So because of many reasons, we opt to high voltage. So 11 kV is used in medium voltage. What is the proportion of virtual synchronous generator that can be used combined with mechanical inertia? Yeah, that is a good question. I will tell you. I can understand where the question coming from. I think, Devin, I think your father is working in CEB. Oh, is it? I don't know. Yes, right. Then, good question. We are thinking of this, but remember, these are still emerging technologies. There is a thing called there's a thing called synthetic inertia, but synthetic inertia and actual mechanical inertia are two different, because synthetic inertia get intervened when it notices a frequency change, whereas mechanical inertia prevent you from changing the frequency. These are two different things. About again virtual synchronous generation, yes, these are all concepts. All these things will come very handy when we go for high renewable, but these are still emerging technologies. That is why I told you we have to first get the system ready. We have to get the grid ready for zero carbon jump, this 100% carbon neutral jump. There are a lot of emerging technologies like this, but trust me, they are not there just yet. They are on technical papers, they are on research, but that is why I said when academics or scientists or visionaries can say anything that they foresee, but when we engineers say that yes, we go for something, it must be both technically and practically possible. These are very promising technologies that are coming up. we are not conducting any research, Devin. We have a R&D branch, but we are keeping a very close eye on these developments, and we are very ready to adopt these technologies. We need them in the future when we are operating a system with very high proportion of renewables. Then about setting aside safety concerns and political issues, nuclear energy. Again, nuclear energy, yes, it is a good option, but we consider it in our long-term generation planning process, but still it is not picked up due to economic reasons. There are two problems with nuclear. One is the smallest plant size, that we call it the package size of nuclear reactors, is still large, right? It's still large. The smaller reactors, though they are practically available, technology is available, we call it the package size reactors, but still since they are not, these are not off-the-shelf products, right? Nuclear power plants are not off-shelf products. The technologies are out there, but still the smallest unit size is still high to our system. Construction periods are very high. It takes about 10 years for you to put up a nuclear power plant. And also taking all the costs into consideration, nuclear power plants have very high capital cost, very low operating costs. So we include it in our planning, long-term generation expansion plan, but if the plan does not pick up nuclear, because still it's not the most economical favorable solution. Now with high renewables, the days of nuclear will even be less. It will be even pushed back into the future, because it's very difficult to operate a renewable system with nuclear, because it has the flexibility is very less. Then I will take the next question. Storage capacity of hydropower station. Existing hydropower station storage capacity is not possible. We do it at Castle Reef. I don't know whether you heard. We increased the storage capacity little by installing what is called flash boards. We increase it about a couple of meters. Yes, Lakshapana Pond, it's not at Lakshapana Pond, but at Castle we do that. But remember, these civil structures must be capable of withstanding the load. So as a result, it's not very straightforward to increase the capacity. According to the long-term generation plan in the CEB, will the duct curve resulted due to renewable penetration result in a negative generation in the baseload future? Yes. That's a good question. In fact, this slide that I was having on the screen is to explain that renewable power plants, particularly the power plants that are connected to the distribution network, we call them embedded power plants, are seen by the system operator as a negative load, right? They are seen as a, let me try to explain this. If my simulation still works, let me try to explain. Now, you have 132 kV system here, and if this is a bridge substation with 2 transformers, we have the 33 kV bus bar here, and let's say we have 2 outgoing feeders, each carrying 10 megawatts. So system operator is operating system at high voltage network. He sees 20 megawatts of demand, which is coming from these 2 10 megawatt feeders. So let's say there is a mini hydro power plant connected to one of the feeders, which is having normally when I switch back my simulation does stop. I will explain verbally. Let's say if this mini hydro power plant is 5 megawatts, when it starts generating 5 megawatts, what happens is these consumers consume from this power plant rather than drawing from the network. So what happens is this 5 megawatt in effect reduces the 5 megawatt coming from this side, and as a result, now the 20 megawatts seen by the system operator is 10 megawatt plus 5 megawatts, 15 megawatts. In fact, the 5 megawatt mini hydro is shown as a 5 megawatt negative load to the system operator. As a result, you are very correct. This has the, now, for example, if all your solar is during this period, when you have more and more solar, it will not show in the load curve, but it shows as a dip in the load curve. So it's a negative load. As a result, yes, there's a very big problem in that, because even now I told you, even with the Sirasa Superstar program, we could operate the system because it is predictable. The night peak, lot of people think the most difficult time period for us to operate the system is night peak. No, it is the off peak. Night peak is not difficult because we know that it is coming and we can have a fair guess how much it is. But with all the renewables in the system, even now we find it very difficult to do a load forecast for the next day, because all the solar and wind, most of them are embedded into the distribution network. As a result, they take part of the consumer demand. We don't know how much of solar we would get in the next day. It's very difficult even with forecasting. We have forecasting at Mena Wind Power Plant, but even that forecasts are not working properly. As a result, the power system operation planning will become very difficult. Remember, I told you about operating with a hydro system. It needs very, very careful planning. Excuse me. This planning requires day ahead. We forecasted the next day demand and we prepare a day ahead plan of 15-minute duration. The starting point of planning is demand. Now demand forecasting has become very difficult because of the embedded generators, particularly solar in the network. So your question is right. There will be impacts on that. I think these are the questions in the chat. So let me open out for any questions that you want to ask directly by anybody from the audience.
Can I ask a question related to what you just said about solar?
Yes. Yes,
I'm looking at it from a solar rooftop point of view. Now, I know a particular installation generally gives about 25 kilowatt hours on a good day. But on a bad day, sometimes next day, it can fall down to 5 kilowatt. Would such large variations occur when you are considering the large system?
Not to the same extent because of geographical spread.
I know. What sort of range can it go to half the value?
Yes, yes, okay. even less than that.
That's right. Yes. So your planning becomes very difficult because you cannot predict in advance even for the next day. Right. Thank you.
I will add something on to that. That you brought a very interesting point. That is why when we develop, now I told you we need about 3,000 megawatts of solar plants. That is why when we develop the solar plants, we have to maintain the geographical spread, because we don't want to develop all the solar resources in the eastern part and then go to the western part. We have to maintain geographical spreading, and also we have to maintain a certain distance between arrays, between solar arrays, so that the single passing cloud would not impact all the solar power plants at one go. So these are things that we have to take into consideration. That is why we said we must go to the 70% renewable gradually. So we still think 230 is too early, but now that the government had given us the go ahead, we have to go because that is government policy. But this is something that we have to go gradually, as I showed you in this diagram, from brown via blue into green, because we are playing with synchronous power systems of machines operating in synchronism. And you all will later learn how when you lose synchronism, when the machines run out of step, what happens inside the machine. One happens with the fields. Your lecturers will tell you, machines started swinging with each other. There is instability, there are transient instabilities. It's very critical, very difficult. We should not play around. That is why even in developed countries like Ireland, even if they have a lot of renewables, they have a real-time asynchronous penetration limit. They don't allow more than 60% of asynchronous technologies to come into a synchronous system. They curtail. They stop generating from solar and wind at any given time when the asynchronous penetration reaches exceed 60%. So there are some limitations like that. We have to improve our grid code in order to make those changes in future. Right. Okay. Open for questions.
Sir,
Yeah, please go ahead.
yeah, so as you mentioned in the beginning of the lecture, if the power demand increases suddenly, to control the frequency, can't it be done automatically without having a person to control the frequency?
Good question. Yes, answer is yes. You will learn in your power system control also. You have to have a tertiary loop. We call it the integral controller. When you learn your power system basics, you will see that these are called integral controllers, which is integrating the frequency error and doing it automatically. It can be done. It can be done. In fact, Upper Kotelawala power station that I have mentioned in my list of power stations that is capable of doing frequency controlling has this option. So older power stations, it is not there built in, but new power stations, it is there. We call it the integral control. Integral because they are using the integration of frequency error. So that is possible. Technically, it is possible. And also, I will add something more that I didn't tell you earlier. In the new system control center, actually they have what we call group control. They have the option of not controlling frequency from one power station at a time, but rather they take about 3-4 power stations together, and they from the system control they send what are called AGC commands, automatic generation control commands, and control these individual power stations so that they are controlled as a group. We call them group control. Because in the future power system, the largest single unit that we have in the current system to do frequency controlling is 171 megawatt Victoria power station. But when your power system grows big in size, that unit will not be able to make an impact to the overall system frequency. It becomes too small. So in those days, you have to use group control. These technologies are available. These are not big things. These technologies are available. Automatic frequency controlling technologies are available. These are not, you will see these in the future power system that you will inherit and work in future. Yes, so your question is yes, it's possible.
Thank you, sir.
Sir, I have a question.
Yeah, please go ahead.
Regarding a real-time control, what will happen if the load demand suddenly increases, like unexpectedly in a rare occurrence during the off-peak time, and while some of the generators are switched off? So what will happen then?
During off-peak, it would not be a problem at all because during off-peak, we have a lot of excess generation, because even during off-peak, let's say by 2 a.m., 3 a.m. in the morning, the demand would be about 1,300 megawatts. But the problem is we have too much of generation, right? We have too much of generation. As a result, for example, our coal plants, each coal unit of 300 megawatts will be deloaded to its minimum stable load, which is 180 megawatts. So during off-peak at about 2 a.m. in the morning, our coal plants each would be running at 180 megawatt each. So that is 540. Then when we add all other power stations, there is enough spinning reserve. There is enough reserve capacity to be taken up in case of an increasing demand. But the big problem is your other side. If you ask the question during off-peak, if the demand reduces all of a sudden, sometimes the coal power station cannot be reduced its demand beyond 180. Sometimes you have to switch off coal mills. So during off-peak, our problem is lowering the demand. During night peak, the problem is increasing the demand. During off-peak, but always when you're operating a power system, you call reserves which can be operated either on increasing side or decreasing side. So we always keep a margin in our generators so that we can decrease the demand, we can decrease generation, so that even if the demand is reduced, we have sufficient generating reserves we call it down regulation, so that we can lower our generation. For example, now our country, the spinning reserve policy is 5%. We have always must have 5% of spinning. Spinning means they are ready to be taken up. They are not fully loaded. The capacity is there, which is on the positive side as well as the negative side. So always when system operators are operating the system, they are mindful of the fact that what you just asked is can be possible. Sometimes about 50, 60 megawatt, even when one large 33 kV feeder trips, one feeder can go up to 20 megawatts, because these feeders are about 400 amperes. They 33 kV, that is 20 megawatts, that is equal to 20 megawatts. So if one fully loaded feeder trips, the load comes down by 20 megawatts. So system operators always keep a margin in their hands to play around for increase and decreasing loads. So yes, we do that. Yes, we are keeping a margin of in generators.
Thank you, sir. Got it.
Ms. Lakshitha, this is Devi. Hello.
Yeah, yes, please go ahead.
Yeah, one question regarding battery energy system storages. In your presentation, you mentioned that you're planning to install battery energy system storages. Now, what is the ramp time period which the CEB is considering when it comes to batteries for primary frequency control? The ramping time, or have you done any research on that? Or
yes, yes. In fact, when we are, I don't have the figures offhand, but these renewable energy integration studies, when they do the renewable energy integration studies, they model the system and see, when they see the largest amount of renewable energy that could be absorbed, they model the system and see when that largest penetration is reached, and when they change, when the solar is ramping down due to a cloud passing above, what is the impact of the system frequency, they model it. So answering your question, batteries are very capable of injecting very high power capacities during very short periods. So batteries are very good devices, but the only problem is battery costs are still very high, but it's rapidly coming down. Batteries are serving for two major purposes. One is battery as a control solution, and second is battery as a storage solution. Remember, I told you the sunny Sunday effect. During 2026, 2027 period, we will start experiencing more generation during certain days than the demand. So during such time, we have to store the excess generation in batteries. Batteries using for storage purposes is very expensive, but batteries using for control purposes is not so expensive. So batteries can inject power in millisecond region. They are very fast, so they are capable of injecting high power capacities. And also, I told you, we are hoping on pump hydros. This pump storage hydropower plant that we are planning is a reversible plant. It's a variable frequency plant. It's not the conventional hydropower plant, where when it is operating at a load, it can also do the frequency controlling. It also can react very fast. So in future, to complement the renewables, our thermal fleet must be very operationally flexible, not like today. If we are going for 70% renewable, 30%, only 30% is allowed for the balance of flexible conventional plants. That 30% must be very flexible. So unfortunately, out of this 30%, we already have our coal plants and combined cycle plants running on LNG. But the future, the generating capacities that we are planning now will be consisting of internal combustion engines. Internal combustion engine can start sometimes within 3-4 minutes. So even instead of keeping your spinning reserve, sometimes you can keep an internal combustion engine shut down, because you can call it up within less than 5 minutes. They are very fast, but they're not very efficient. So these internal combustion engines will be fired using LNG. There are LNG fired internal combustion engines, and also gas turbines, and also batteries. So these three technologies will be used in future. for these very short-term power injections and pump storage hydro, both in pumping mode and generating mode. So they will take up any changes by the renewable. I will also tell you another thing. Now, a lot of people think that since we have a lot of hydros, the hydros can do take up the variation. Yes and no. No, one reason you know already by now that we cannot use hydro system the way we want. But even if we can, there is a problem because our hydro actuators are not designed to do the regular change. There is frequent wear and tear in our hydro machines. The problem is when all the solar and wind plants are varying, we call it the intermittency, which is first reflected in the system as a change in the frequency, but you will hardly notice in the frequency plot because these frequency changes are immediately taken up by hydro machines and are offset. But that is not good for the machines. So right now, the first hit is taken by the hydro machines, but in our future system that we are planning, we intend to let the batteries take the first hit, and we intend to introduce a small deadband into the governors of hydro machines. You will later learn all these things when you are learning power system control. You can introduce purposely you can introduce a deadband so that your hydro governors don't react. Even though they can react, they don't react. They wait for the batteries to come. Batteries will take the first hit. They will cushion out the immediate second to second intermittencies. Then the hydro power stations will slowly come up. So batteries, they are quite capable of giving very high ramp up down rates. The figures I cannot remember, but it varies from battery technology to technology, but they are quite capable, and we are hoping to rely on batteries to do this controlling in future.
In what voltage level are you planning to install battery energy system storage, and are these distributed or closer to any other renewable reserves?
We are exploring all the options. That is also a good question. We will be distributed throughout the country because I will also tell you something else. Since now, for example, solar power has a very low plant factor, right? Solar plant factors are less than 20%. As a result, for example, if you generate the same amount of energy from a 300 megawatt LNG plant, you need 1000 megawatts of solar power, 1000 megawatt of solar power. That means the transmission network that we now want to design for 300 megawatt, in the future to get the same energy, that must be capable of transmitting 1000 megawatts. So that means we have to go for 400 kV. The renewables, a lot of people think renewables are cheap, but in order to facilitate renewables, there are a lot of investments. But one way of overcoming this is by installing distributed batteries so that all the generation from solar all of a sudden don't come directly to the transmission network. They are stored in the batteries at those locations and gradually released. So that is why in that sense, batteries will be distributed throughout the country. Some of the batteries we intend to work alongside the renewable technology, because in future all the developed countries who have gone for large high proportion of renewables, they don't allow these renewable power plants to inject power at any quality they like. They want these power plants itself to control their renewable output by installing their own batteries. So there are batteries are also coupled with renewable power plants in the future with solar and wind, and doing some control at the terminal itself and injecting power at some quality than as right now to the grid. In addition, we have to have grid level battery also installed by us, which are mostly distributed throughout the country. So we will have both types. We have batteries installed with power plants. Remember, then the renewable cost goes up. They are no longer cheap. And we also have to have batteries installed in they are called grid level storage. We have to have grid level storage as well as we have to have resource level storage in both when you are going for high proportional renewables. If you have any follow-up questions, please ask if you have any further clarification.
Thank you very much.
If you have any questions, I can answer, or the moderators can think when they want to. I can wait. I told you, but you can decide. I need to answer your questions.
Seems like there are no more questions. So for further information, please refer the link of our Instagram profile in the chat box. And now I cordially invite our Secretary, Dhanuri Udadeniya, to deliver the vote of thanks. Over to you, Dhanuri.
Thank you. Good evening. Guest speaker for the day, ENG.Lakshitha Weerasinghe, Head of the Department, Electrical, Electronics and Telecommunication Engineering, and Advisor of the Power and Energy Society, Captain Kanesh Dadalage, Senior Professor J.R. Lucas, lecturers and instructors, fellow senior brothers and sisters, and dear fellow undergraduates who are present here today. On behalf of the Power and Energy Society and my own behalf, I would like to extend my gratitude to Deputy General Manager, Transmission and Generation Planning of Ceylon Electricity Board, ENG.Lakshitha Weerasinghe, for considering our invitation and spending your valuable time for us. We all gained vast knowledge about the present and future of Sri Lankan power systems. I would also like to express my sincere thanks to all the lecturers of the Department of Electrical, Electronics and Telecommunication Engineering present here today and all the seniors of Faculty of Engineering. I would like to thank all the participants, including the day scholars and officer cadets of Faculty of Engineering for being here today. Finally, I extend my thanks to all the committee members who did support us in every possible way. Thank you.
We have reached the end of the session. Now, we would like to invite you to a group photograph. So please turn on your cameras if possible. Thank you. Thank you all for joining. Good night and stay safe.
Good night. Thank you.
Good night.
Thank you.